Hello and welcome to the YouTube video lecture 13 of group theory. We start with recalling what we have done so far. We have seen in the last lecture, we have seen Cayley's theorem. Before Cayley's theorem, what we had seen was this maps. So let us recall. So we started with G is a group and we took one element G in G. So when we start with one element G in G, what we defined was we defined tau G from G to G by, if you remember, this is tau G of x equals to Gx. Capital TG, we had defined the inner automorphism, TG of x equals to Gx G inverse. So it is very similar, tau G of x equals to Gx for all x in G. Then what we observed that this tau G is not automorphism, but it is 1, 1 on 2 function. So tau G is in AG. So that is this set so that G belongs to G. This is a subset of AG. That means if I take any element in G, I get an element tau G in AG. So that inspires us to define a map. So we defined a map that was psi from G to AG, right? So by, how did we define? Psi of G equals to tau G. Psi of G equals to tau G. So when we have an element in G, we have a 1, 1 on 2 function tau G, and this led us to Cayley's theorem. We showed that psi is an isomorphism. So that means tau GH. So we take two elements, GH, G and H in G, and then we take GH. So tau GH is same as tau G composition tau H. That is homomorphism part, and then tau G equals to tau H. That means psi G equals to psi H. Then we have G equals to H. So psi is isomorphism. It need not be onto. So that means this G is embedded. I mean, it is isomorphic to a subgroup of AG, which was nothing but Cayley's theorem. So what we had seen, this psi we had defined in the proof of Cayley theorem. Every group is isomorphic to a subgroup of AS for some set S. So in fact here we take S equals to G itself. So what we show is that G is isomorphic to a subgroup of AG. So in fact here we take S equals to G. Right, so we have defined this, and yeah, so that means for every G in G there is a map tau G, and that is in AG. So now we had considered this tau G of x equals to Gx. So this was map on G. Now we consider a map on a smaller set, not the group itself, but a smaller collection. So we take cosets of some subgroup in G. So what we do is next in the next lemma, this is what we have seen. All this we had seen last time. So in this lemma, what we take, we start with G is a group. We take H is a subgroup of G. H is subgroup. S is the set of all left cosets of H in G. So X belongs to G. So set of all left cosets of H in G. And then just like Cayley's theorem, I mean, if we take G belongs to G, then define. So for G belongs to G, we define small tg, that is not from G to G but from S to S. So we are taking not tgx equals to gx, but by, how did we define Tg of x नहीं आवे, what will come is a left coset, so xh equals to gxh, and gxh is also another left coset, so it is an x. Then what we observed, so then we had all this conclusion, if you remember, all these baby exercises, that first of all this Tg belongs to as, right? It's a function from S to S, as, so 1, 1 and 1, 2 for all G in G. So this was first thing. Second is theta, if we define. So for every G, see now for every G we are getting Tg. So that means we can define theta from G to As. If I take an element here in G in G, I get Tg. Tg is in As. So by theta of G, how it is defined? So that is defined as Tg is a homomorphism. This was second exercise, and then third one. So all this is a lemma which are just broken into parts, and this proof we had seen last time. Third one was kernel of theta is the largest normal subgroup. So now largest normal subgroup of G contained in H. So kernel of theta is subset of H. Kernel of theta is normal in G, and it is largest. So if n is subset of H, n is normal in G, then n must be contained in kernel of theta. That means kernel of theta is the largest one. So this is what we had seen, and as a corollary, which was left as an exercise. So as a corollary we have, so this is where our today's video begins. Right, so as a corollary, suppose H is a subgroup of a finite group G. This is what I stated, and I asked you as exercise. So let H be a subgroup of a finite group G, and so if order of G does not divide index of H factorial, if order of G does not divide index of H factorial, then H must contain, so H must have a subgroup N which is other than identity, such that N is normal in G. And this has applications which we are going to see in the next unit, and this is very important. So what, in other words, what we can say, so in other words, if order of G does not divide index of H factorial of index of H, then H contains a non-trivial, so n is not E identity, that means n is non-trivial subgroup of normal subgroup of G. So H contains a non-trivial normal subgroup of G, and as you will see in the next unit, finding proper normal subgroups of a group is also important in some cases, to show that G is not simple. We are not going to that definition right now. We'll come to that, but for that this result is important. So we'll see a couple of examples of this. So then H contains a non-trivial normal subgroup of G. So this normal subgroup N of G. Sorry. Normal subgroup N of G. right? So let us see the proof of this before we see examples. So now see in the lemma, here itself we have a normal subgroup, kernel of theta. As you can see, the kernel of theta is normal subgroup of G, and it is contained in H. So kernel of theta is also here also. It is the same thing. So what we do is we take set S as in above. So take S equals to XH, so that X belongs to G. So let S be the set of all left cosets of H in G. We are given H is a subgroup of finite group G. So again, as above, S is the set of all left cosets, and what we take is same as above. We define theta from where to where? Theta from G to AS, as we had defined above, as in above lemma. So how do we define? We define theta of G equals to TG, just as in above lemma, right? So then we know that, then by above lemma, what we know? So by above lemma, we note that kernel of first of all, theta is a homomorphism. Theta is a homomorphism, and kernel of theta is a normal subgroup, and kernel of theta is contained in H, or directly write kernel of theta is a normal subgroup of G contained in H. So this could be our n. If you want, we can take this as our n. N equals to kernel of theta. Then what we have, n is contained in H, and it is a normal subgroup of G. Both things are achieved, but only thing what remains. So H is a subgroup of a finite group G. Then H must have. So H must contain. So n is a normal subgroup of G here, and H must have subgroup. So H contains, as we said, H contains a non-trivial normal subgroup n of G. So here also, but only thing to prove here remaining is we need to prove this non-trivial. So this is the trick. So if we want to take kernel of theta equals to n to be the normal subgroup contained in H, we are done. Only thing what we have to show that kernel of theta is non-trivial, right? But what we have not used so far in the theorem, so far we have not used this fact. We have not used the fact that index order of G does not divide index of H factorial, and using that fact we will show that kernel of theta is non-trivial. So theta is homomorphism. So kernel of theta is non-trivial. That means suppose theta is an isomorphism. Suppose kernel of theta is trivial, then what happens? So we take n equals to kernel of theta, then n is subset of H, n is normal in G. So it remains to show that n is non-trivial. So that is kernel of theta is non-trivial. So suppose if possible kernel of theta is trivial. Suppose if possible kernel of theta, which we have taken n, suppose this is trivial, then that means then theta is an isomorphism, because theta was already a homomorphism, and if kernel of theta is a singleton identity, that means theta is right, since kernel of theta equals to identity implies theta is 1 1. and theta is already a homomorphism. So 1 1 in homomorphism, therefore theta is an isomorphism. And if theta is an isomorphism from G to AS. So if theta from G to AS is an isomorphism, see, remember it is not onto, it is 1 1 and it is a homomorphism, that much we know. We don't know it is onto or not, so onto we cannot say, but isomorphism we know. So theta is isomorphism. Then what can we say? Then we can say that G is isomorphic to theta of AS. Right? We cannot say G is isomorphic to AS. G is isomorphic to AS, we can say only when theta is onto 1 1 and onto function. So onto we don't know. So G is isomorphic to theta of AS. That means it is isomorphic to a subgroup of AS, image of AS, as we had seen above. Or we can say that order of G equals to order of theta of AS. Yeah. Oh, not theta of AS, theta of G. Right. So this is G is isomorphic to theta of G, which is a subgroup of AS. So this is theta of G. Order of G is same as order of theta of G. So theta of G is in AS. So not theta of AS. Sorry, that is theta of G. Yeah. So if they have same order, that means order of theta G, we can say that order of theta G is what? It is subgroup of AS. So order of theta G divides order of AS. It is finite group, so we can write order of AS. Otherwise, AS is infinite if S is infinite. But the group is finite, so number of cosets are finite, and therefore AS is a finite thing. So this is by Lagrange's theorem. Order of subgroup divides order of group. So we have order of theta G divides order of AS by Lagrange's theorem, but order of theta G is same as order of G. So we say that order of G divides order of AS. The reason is since order of G is same as order of theta of G. 1, 2, yes, and then this bracket. Okay, but what is order of, so therefore order of G divides, what is order of AS? AS, how many, what is the order of AS? If S has n elements, if cardinality of S is n, we know that then this implies order of AS. 1 1 and 2 functions કેટલા હોય? So these are n factorial, this we know, right? So this we know. So what is AS? AS is the, so S is this. So S is the set of all left cosets. So what is the cardinality of S? Cardinality of S is n, then cardinality of AS is n factorial. So here the cardinality of S, that means the number of distinct left cosets of H in G. So cardinality of S is index of H in G. But then what is cardinality of AS? That is n factorial. So this is n factorial, and which is a contradiction. This is a contradiction. So here we are having contradiction to our assumption. Or to the hypothesis, contradiction to, not we have not assumed, but it is contradiction to the fact that we are given order of G does not divide index of H factorial. This is what we are given, this one. So we are now using this, order of G does not divide index of H factorial. If this is the case, so this is a contradiction, because here we are getting order of G divides index of H factorial. Right? How did we get index of H factorial? This is nothing but index S, cardinality of S is nothing but index of H, as S is a set of all left cosets. So this is contradiction. Therefore kernel of theta, therefore n equals to kernel of theta, and this is non-trivial. So hence H contains a non-trivial normal subgroup N of G. So H has a normal subgroup. N is subgroup of H. H is subgroup of G. But N is normal in G, not in H. N is normal in G. So this is the proof which I had asked you to do. But anyway, this I am giving in the video itself. Okay, so now let us consider some applications as what I said. So as an application of the above corollary, we discussed two examples here. So let us take example 1. Suppose G is a group of order 36. So let G be a group of order 36, right? And H, let H be a subgroup of G. H be a subgroup of G of order 9. Now the question is whether such a subgroup exists or not. 36 order group, will it always have a subgroup of order 9? Is it true or no? So it is true. It is true in general, which we'll prove later. So this will see. We shall see that. So we don't bother right now. Assume that H is a subgroup of G of order 9. So we shall see that it is always the case. This means what? That means a group of order 36 will always have a subgroup of order 9. मिलेगा ही उसको. Any group of order 36, abelian, non-abelian, it will always have a subgroup of order 9. So that is always the case. So then what is index of H? This is if no finite group, so index of H is nothing but order of G upon order of H. This is order of G upon so order of H, which is we know what is that, 36 by 9, and so this is 4. Okay, so index is 4. Then what is index of H factorial? This is 4 factorial, which is 24, and order of G is given to be 36. So order of G, it does not divide index of H factorial, right? 36 does not divide 24. So which is so I can say that 24 is less than 36, which is same as order of G. So order of G does not divide the index of H factorial. That means then by the above corollary, H has a subgroup, right? H has a subgroup which is N, which is non-trivial, such that N is normal in G. H contains a non-trivial, so N is non-trivial. It is contained in H. N is subset of H, and a non-trivial normal subgroup of G. So N is normal in G, such that N is a normal subgroup of G. So N, so order of N divides order of H, which is 9. So this implies order of N can be 3 or 9. 1 it cannot be because it is non-trivial. So since the order of N, it is not equals to 1. So it is either 3 or 9. So if order of N equals to 9, then N equals to H, subgroup of H of order 9. So and H also has 9 elements, so then N equals to H. And in this case H is normal in G. In this case we can conclude that H is normal in G. right? So in this case, we can conclude that H is normal in G. When? If order of n is 9, so n equals to H. So n and H are same. And so n is normal in G, so H is also normal in G. But otherwise, we cannot say that whether H is normal in G or not. So given a group and its subgroup, whether we can tell that it is normal in G or not. In this case, at least we cannot tell, but at least what we know, G has a proper normal subgroup. Right? 36 order group has a proper normal subgroup, and n is the proper normal subgroup of G, whose order is 36. Order of n can be either 3 or order of n can be 9. So this much we can conclude. So this is example number 1, and now let us take example number 2. So in example 2, let us consider a group of order. Let me take this same example which we have written in the notes, which is given in Herstein. So let G be a group of order 99. So let H be a subgroup of order 11. So G is a group of order 99 and H is a subgroup of order 11. Again, what is the guarantee that it will have a subgroup of order 11? We'll see that, but we can even right now also tell, because we have seen Cauchy's theorem for abelian groups, we have seen, but not for non-abelian group. But it is true, as I said, Cauchy's theorem. So this, if and in fact, this will be an abelian group. But let us so far to give an argument why it will have a subgroup of order 11. We can say that by Cauchy's theorem. We have not seen the non-abelian case, so I cannot use it right now. But let me still allow me to go further ahead and then use this result, because we know it is true. We are not yet proved, but we can also prove by other means also that a group of order 99 will always have a subgroup of order 11. So in fact, it will have a unique subgroup of order 11. But by Cauchy's theorem, H has an element, right? 11 is a prime. Cauchy's theorem says that P divides order of group, then G has an element of that order. So 11 divides 99. So H has an element, not H, G has an element. G has an element A of order 11. And then take H equals to the cyclic subgroup generated by A. So then order of H equals to 11. So it has G has an element of order 11. Suppose that, call it A. Then we generate a subgroup of order 11 by that A square, A cube up to A power 10. Then A power 11 is again identity. Then A n. So cyclic subgroup generated by that element of order 11. So that is the 11 order subgroup. So it always exists. So what two things we have? G is a group of order 99 and H is a subgroup of order 9. So then what is index of H then? Index of H in G, this is again it is finite, so we can write like this. So 99, which is 9, and 99 does not divide 9 factorial. So that is order of G does not divide order of not order but index of H factorial. Why? See, 11 divides 99, but 9 factorial is what? It is 1 into 2 into 3 up to 9. So 11 divides left hand side. So if 11 divides this, 11 must divide 9 factorial, but it cannot divide 9 factorial. There is no prime 11 here. So order of G does not divide index of H factorial. So by above corollary, what we can say, H contains a subgroup, H contains a subgroup N which is non-trivial such that N is normal in G. So then H contains a subgroup which is normal in G. But now n is subgroup of H. N is normal in G, but n is subgroup of H. So order of n divides order of H, which is 11. So that this implies order of n is either 1 or 11. But it cannot be 1 because n is non-trivial. Because n is non-trivial, this is not possible. So that means, but order of n is not 1, and so order of n equals to 11, and hence we have h n equals to h because h is also a group subgroup of order 11 and n is subgroup of h of order 11. N is subset of h, it also has 11 elements, h has 11 elements. So in this case n is normal in G and therefore h is normal in G. In this case h is normal in G. So what we had concluded here, 99 order group has a normal subgroup of order 11. So this subgroup which we have taken of order 11, it will always be normal in G. So that means a group of order 99 will have a normal subgroup of order 11, or in other words, the 11 order group, the subgroup of order 11 of order 11 in a group of order 99 is normal. Is always normal. Right? So in this case, at least we can actually conclude that H is normal in G. In other case, H has a subgroup which is normal in G, and that subgroup had order 3 or 9 in the previous case. It had 36, so it had order 3 or 9 as we have seen. So if it is 9, then n equals to h. Otherwise, it is not the same. Right? So let me pause here.